sense of it. So totality is the system. Now, obviously, you're going to read the paper before the final. And there's very little that I'm going to say that isn't in the paper, apart from providing context. But still, these lectures are good. They will help. Okay, so we kind of set this up at the end of class, and I ran out of time last time. But I had said, there was this thought experiment in which I said, imagine you had a fleet of computers whose combined processing power you would like to exploit in the best way possible. And that, as is often the case in real life, although maybe not in our idealized models, the input data of record is already sort of massively distributed on these machines, although not laid out or placed in any particularly intelligent way. The idea is that the input data set for some massively parallel computation is already on the computers that happen to have the compute. Right? So computers have disks, they have memory, they have CPUs. It's very often the case that there's already stuff on the disk. Now, why in real life does this happen? Like, why would the data magically already be distributed? Why don't you have this problem where you have some big database and now you want to do parallel compute, you have to break it up into pieces and send it to everybody like you're doing in your assignment. So sometimes, obviously, you have to do that. And in fact, in MapReduce, you even have to do that in the second phase. But you very often don't have to do it in the first phase. Why is that? Like, why would the data already be distributed?
If the clients are from different regions of the world, then they're writing to their local cache, right?
Yeah, so it could be basically like, because the computation that produced the data may already have been massively distributed, and people may have written out things to their local disks. Like, the most obvious example is like almost any website that you can think of has sort of like a front end that's a bunch of stateless web servers that are fronting some middle tier, behind which is some databases probably. Like, this is like what Facebook's architecture looks like, for example. There's a middle tier that has some cache and it has some state. It flushes, writes back to some persistent databases. And then the application logic lives on these stateless application servers. Now, each of these stateless application servers is dealing with lots of concurrent traffic from lots of clients, and they're writing out some little, Apache or Nginx log. Which means that these servers have massively distributed logs characterizing all the activity that's happening in Facebook sort of already. So this is an opportunity to move the computation to where the data already is, so that you don't have to pay a data movement cost right off the bat. Right? And when we did this exercise at the end of class on Wednesday, we came up with a damn good provisional solution. Does anybody want to summarize what that solution looked like? That's just like a three-step thing. We won't have to go too detailed, but anybody want to summarize? It could be you, or it could be somebody else. It could be you. No, you don't have to come up here, but just.
You do all the work separately on each computer, and then combine the results and then partition the results across the computer.
Yeah. Do all the work you can. Locally. And what you said was, why don't I just like come up with a word, count list on a per server basis? Do all the work you can locally. And by locally, I mean without communicating with anybody. Earlier in this course, I talked about algorithms that were embarrassingly parallel. Do you remember that? The idea of an embarrassingly parallel algorithm is an algorithm for which the data is already broken up, and the data doesn't need to be combined afterwards. So solving this algorithm would just involve breaking the algorithm up into pieces and running them all in parallel. And when the algorithm completes on all the servers, you're literally done. That's embarrassing parallelism. And you shouldn't be embarrassed. Like, it's awesome when you can get that kind of parallelism. It's called embarrassing because it's not hard enough for like theorists to figure out how to do. It should be called awesome parallelism. And the insight here is that, like, at least from Google, is that a great many practical data-intensive tasks begin with a massively embarrassingly parallel part. And this is an example of that. You can do almost all of the work without anybody talking. Unfortunately, to do the last bit of work, everybody needs to talk to everybody. Shuffle the data around the network so that the data's in the right place. In particular, in the context of our word count example, that means, let's imagine that these are the servers, and we said, this server is kind of broken into two pieces. The piece doing the massively parallel part, and the piece doing this other part. So what that means is that let's imagine that this piece is now responsible for the words the and the words lazy, and they're going to try to get those totals. What that means is that this guy probably has the word the in his list, because it probably occurred in one of his documents. It means he needs to send some data. Some data needs to move from here to here, and from here to here, and from here to here, and from here to here. Those are all the thes. And similarly, everybody is going to have to talk to everybody. What this is, another word for this is a repartitioning. In assignment 4, you are partitioning or sharding your key value store on the keys. The idea being one key goes to one server, right? You're partitioning on the keys. In this toy example, we began with the data partitioned by document. A particular document is on two machines, I said, for replication reasons, but if you ignore that for a moment. We've in some sense hashed the documents on the servers. But for the second half of the computation, we want to hash the words on the servers, which means we need to rehash. We need to partition the data again and shuffle all the data around the network. We hope that there will be less data moved around in this phase than there is data processed in this phase, and that's certainly the case in this computation, right? Because the set of counts is just much smaller than the documents they came from, right? And then the final stage is combine information that came from multiple inputs. And so obviously, this is where all the communication happens. And all that communication happens so that we can combine things, so that we can say, well, this guy said there were 50 thus, and this guy said there were 100 thus, and this guy said there were 50 thus. Therefore, there's 200 thus. Right? We couldn't have done the combine without the shuffle. Yeah? So this is kind of the high-level idea, is that so many of the things that take lots of computers to process begin with distributed data, have a massively parallel phase, then need to send the data everywhere and reconfigure. So, why don't we come up with a framework that does all of this for you, but doesn't specify the work that you do locally, and it doesn't specify how you combine. Right? So in our word count example, the work here was tokenize, right? Break up the document into words. And down here, the work was plus, right? Add integers to each other. So in some sense, the programmer just had to supply, how do I tokenize a document? And how do I add two numbers together? And we do the rest. And we take care of scheduling the computation so we don't do any extra work. We're going to take care of scheduling the communication so you don't need to think about computer communicating. You don't need to think about distribution. You just need to write a pair of functions that you could run on your laptop, and we'll go ahead and run it on a million laptops. We'll also make sure that if we're running it on a million laptops, surely, a million computers, surely one of those computers will fail. And because we expect this computation to be relatively long, it doesn't make sense to just restart the computation if there's a failure. We might never finish. Right? The computation takes like 6 hours, and it's likely that a computer will fail. You could be running it forever, which means this system needs to be transparently fault tolerant. If machines fail, you need to just kind of keep going without them. Right? But you have to compute the correct result, which, as we learned in this class, is like super duper hard if what you're doing is some general purpose computation. When MapReduce come up with a programming model where they were constraining so much what you're allowed to say in those boxes that we can ensure transparent fault tolerance. We also want it to go fast. And making it go fast is going to involve exploiting two really important things in the data center. The first is locality, right? The idea that we've already sort of talked about this a little bit. Data has gravity. It costs time and bandwidth to move data from one place to another. Computation has much less gravity than data. You just need to describe the function, the lambda that runs on the data. So whenever possible, you want to schedule the computation as close to the data as you can, so that you have to move the data as little as possible. But this isn't always easy, right? Because what if my fleet was laid out in such a way, and this could certainly happen, remember, because we have no control over the placement of the documents, that there's documents everywhere. But a particular job that I want to do only wants to work on a subset of the documents. So let's say the documents with X's on them are the documents that I want to work on. Okay, so now let's say I have some kind of scheduler. I haven't said anything about MapReduce yet. This is all strong and stuff. But I have some kind of scheduler trying to figure out who should do the work. What computers should do the work, right? So scheduler has options to say, I want to place a task close to the data that it's going to process so that there's no data movement penalty. That's great, right? I want to do that whenever I can. However, in this scenario, it wouldn't be a great idea to schedule many dozens of tasks close to the data. Because then this computer will be overutilized and these computers will be underutilized, and the whole computation will go as slow as this computer. Right? We need to spread the data around the computers to go fast. But we also need to keep the computation close to the data to go fast, right? So this is kind of a multi-objective optimization problem that the scheduler has to solve. In a scenario like this, the scheduler has to figure out what balance of, okay, in some cases I'm going to schedule the task with the data. Maybe I'll schedule one more task with the data. Now this guy's overutilized. Now I'm going to schedule a task close to the data that has to fetch the data remotely. And now maybe I'll, or sorry, it had to do that one anyway. But I'm going to like schedule another task close to the data, and I'm going to schedule another task over here that fetches the data. You see what I'm doing? So like, it's hard. Right? So we're trying to minimize the movement of the data, and also minimize the skew in the number of tasks placed on a particular computer. So it's not easy stuff. So reasoning about locality and uniformity of load. And then this other really important problem that happens in systems involving a great many computers. Some computers process slower than others for a variety of reasons. I mean, in real world clusters, the reason might just be heterogeneous infrastructure. Like you might have some older servers and some newer servers, and the older servers aren't as fast as newer servers. Or it might be the case that you have what's called limpware. So a colleague of mine at Chicago actually coined this term. Sometimes when you're a researcher, one of the things you want to do is coin a term, so that when everybody else uses the term, you have to like cite your paper when you coin the term, and your citation count goes up. So he coined these terms, limpware and limplock. And the idea is that like sometimes hardware just goes like an order of magnitude slower than it should. Sometimes you have a gigabit card that's pushing 100 megabits a second. Nobody knows why. Or sometimes you have a gigabit card that's pushing 100 megabits a second for like a week and then it goes back again. Or you have a disk that's slower than the other disks or whatever. What this means is if you have a limping machine, it's a weakest link or a potato bag race thing where like your whole computation, if you're not careful, is going to go as slow as the limping machine, right? If that limping machine was in some kind of critical point in the topology, guess what? Everybody's pushing 100 megabits a second instead of a gigabit a second, right? So this idea is called stragglers. Right? If I have this race and like most of the machines are going really good, there's this one guy. Guess when we finish? When the tortoise gets there. So you have to mitigate the effect of stragglers. And if you're running your computation on 10,000 computers, the odds are good that one of them is going to be slower than the others. So how do you make sure that you don't always go as slow as the slowest guy? Matt Reese has a really nice answer to this that we'll talk about at the end of class. Okay.
Just kill that.
Programming. Okay. These are the sort of fuzzy systems people type signatures of the map and reduce functions as the authors of the map and reduce paper gave to us. So let's try to unpack this. What does this mean? The user is going to supply two pure functions, right, to fill in these holes. First, a function called map. Who's used Lisp or a Lisp?
Lisp?
Lisp or a scheme or a
Like
racket.
a
Yeah,
Lisp.
so you know map.
So
You know
stick with
map, right? What is
parentheses.
map? Somebody tell me what map is in Lisp or a Lisp. Yeah.
Apply function to every element of the list.
Yeah, so given a list and some function that can be applied to those elements, return the list that you get by applying that function to every element of the list, right? In this case, we're going to allow the map function to change the return type. I guess we did anyway, right, in map. It was all the time with the function cookies. The idea is that we're always operating over key value pairs. So map is going to take as input key value pairs in a particular format of keys type K1 and V1. And it's going to return a list of key value pairs of different types, K2 and V2. And the intuition for this is that map is going to work both like map in Lisp and like flat map in Lisp. That sometimes we're going to want the resulting output array to have more elements than the input array. Right? The intuition here for word count is sometimes I want to take a sentence, the fat brown dog jumped over the lazy fox. No, that's not right. But whatever. The fat brown dog, da 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 da. My input is a document, you know. So the key is like, I don't know, document 1, which is maybe like the URL of the document or something like that. And the value is the complete contents of the document, right? But what we want to come out the other side is the word the and the number 1. The word fat and the number 1. So one key value pair comes in, but very many potentially come out. Okay? So that's what's happening in this. Now, it might just be 1 and 1, and then it would look just like the map function from Lisp, but it might be 1 and many, because you might be doing something like tokenization. Does this make sense? So you might have more values coming out of your map function than went in. In fact, the common cases that you do. Does this make sense? So it's like flat map. So that's it. So maybe we'll take a minute and write down what the map function might look like if we were trying to do a word count, right? It would look like this. For each word in the document, or actually we'll just say given, let's say K1, V1, for each word in V1, the document, emit word, comma 1. That's it. Make sense? So it says, you're given a URL and the contents of the document. What you do is tokenize the document, and for each word in it, you output word and the number 1. Right? So you start out with stuff like this: 1, fat 1. Make sense? Yeah.
What do you mean by emit?
Well, I mean, you know, like as in like a coroutine, like in Ruby emitting, or you can imagine. This is how the author wrote it. You could have imagined saying, let foo, you know, be some empty array, and then I could say foo dot push word, comma 1, and then at the end I could say return foo. This is just an easier way to do that. Right? So like the idea is like as I emit things, I'm consing up an array that gets returned at the end. You never seen this kind of thing in like coroutine programs like Ruby or anything? Yeah.
So we're not summing the counts of the words?
Absolutely not, because, well, good question. So there's an optimization that some of you intuited, which is like, if you did this, you'd be sending the 1 across the network an awful lot of times. And there's an opportunity to consolidate some of those thes on the local machines before you send it out. So because you went there, I'm going to say, in the MapReduce paper, they do talk about a step 1.5 called combine, where if the programmer has given you an assertion that their reduce function is associative, because you can't tell, or maybe you can, Lindsay, I don't know, but MapReduce authors assume that you couldn't possibly tell if a reduce function supplied by a programmer, opaque like it is associative, but the programmer tells you it is associative, then MapReduce will run the reduce function on the mappers real quick too, to get that word list cooked out, as an optimization. If the reduce function isn't associative, this might be a bad idea, so it doesn't do it by default. Okay, so that's what the map function might look like, okay? And then, so what does the reduce function do? Well, the reduce function is invoked with a single key, like the, and a list, single key, and a list of values, 1, 1, 1, 1, 1, 1, 1, 1, 1, and it is supposed to return a single list of these two, is that right?
Seems like you're looking at a P3 or something, right?
No, that's what it says.
Oh, weird.
Let's go list K2, list of V2. could return a list of V2, sometimes a singleton list. Who cares about the type signature? So what might reduce look like? Reduce might, let me double check this. Yeah, sure. It might say, reduce K2, and given it like an iterator of the V2s, it would say result, I don't know, equals 0 for each V in V2. Res plus equals V, return res. Yep. Or emit res as a string. Right, so what happened? We're given a key, the, and a whole bunch of numbers, and we add them together. And we return. Right, so this is a really fancy way of saying sum them up, please. Right, so you wrote, whoops, you wrote this, and you wrote this. And MapReduce is going to schedule them at just the right time to produce the correct result without you having to worry about it going fast and completing the type failures. Questions?
I have a question.
Yeah.
So I'm curious about what you just said about the reduce function having to be associative if you're going to do it locally. Because wouldn't it have to be associative anyway?
Why would it have to be associated?
Because it's a reduce.
But it's not a functional reduce, right? I mean, in particular, when you write your reduce, I haven't talked about this yet, but when you write your reduce, you may assume that the list is in sorted order. And you might be doing some particular computation, assuming something about, hey, if I see, you know, if I see the number 3 and I see the number 4, that's the last 3 I'm going to see, or something like that. And you might have encoded that into your reduce function.
Okay.
And we have this contract from the system because the mappers are going to write out sorted runs, and the reducers are going to sort the things before they do anything. And so I think if it were a true reduce, you wouldn't care what order the things came in all. You wouldn't have to perform any sorts. Right?
Okay, so in general, you can't do this combining stuff locally as much as possible unless you have this
Unless you have this contract.
programmer specified guarantee that it's succeeded.
Right.
Okay.
I mean, I think another way of saying that though is that maybe most reduces should be associative, and maybe people are crazy to not make them associative, and maybe the rule of thumb should be. So you can make this different. This is like the whole thing. You could think you did a perfectly good job of making it associative, and still it's screwed up. You need some kind of tooling help, I think, at the end of the day. Okay, so we talked about the programming model. That seems relatively easy to use, right? Should we? Yeah, heck. Before we talk about the actual architecture and communication model and how this all works, let's talk about some programs that you could write. So Google gives this list of like common programs. We talked about a couple of them at the end of the day on Wednesday. So one obvious one that I mentioned briefly is like distributed grep. Okay, so who uses grep? Grep's awesome, right? Wouldn't it be really awesome to run grep on hundreds of thousands of files, millions of files on hundreds of thousands of computers automatically? That would be sick, right? So how would you do that in MapReduce? Like what map function would you write? And what reduce function would you write? Think about it for a minute. Yeah.
In the reduce, where are you using the K2?
I'm not. I'm not, but K2 was like the word the. Well, like, you could use it, I just didn't use it in this particular function. In your reduce function, you might want to use it, right? What do y'all think?
Should we tell every system to do their own mapping and then do the optimization you were talking about earlier and then combine that up?
No, I'm just saying, like, what would the text in the map function and the reduce function be? Right? Because we don't need to tell the system what to do. The system's just going to do it. All we need to tell the system is what to do in the map and what to do in the reduce.
For the map function, for every file in a system executes grep. Wait,
Yeah, but that's cheating. You know, we don't need to open up a shell, right? Because we know that we're going to be handed v1, the string contents of the document. So why would I open up a shell and invoke it on k1 when I could just do something with v1? Yeah.
So for every line in V1.
Yeah. So like for each line, yeah, you're right. So for each line in v1, what?
If the line, or if the word is in the line.
If word, I don't know, in
You do.
line, okay, this is your favorite regex, don't make me write it, right?
Oh, yeah.
If the word's in the line,
Yeah, I mean,
then
as an
what?
input, right? Then emit the line.
Emit the line, right? That's what grep does,
Yeah.
right? Emit the line that
It's got
contains the
some, like,
word.
fancy
Maybe highlight the word or
Yeah.
something, I don't know, right? And then what do you do for the reduce?
You kind of have to define it, right? Like,
It's the identity function, right? You're like, return k2, whatever. Like return whatever that was, just return it. Because all reduce doesn't need to combine anything, right? Grep is embarrassingly powerful,
oh yeah.
right? So that was too easy, because we can do all the work, literally all the work, locally. Yeah.
Would that return duplicate lines, though?
Why would we want to duplicate lines?
I mean, if you have a line that has the word twice in it, then it will
So-
pronounce twice.
If you have two of the
No,
same
but remember,
line,
there's just
the
one word
is
that we're
in it.
looking for, right? So remember, like, we could have just written a custom function that the word was literally hard-coded. More likely than that, since we would probably want to use this more than once, we make it a parameter or something like that to map. But there's only one word that we're looking at. And if the word occurs in more than one line, we want it to output more than one line. So why are we concerned that it would output the same line more than once?
Saying the word is twice in one line.
What's that?
Was it if the word is twice in one line?
We don't care which.
If the word occurs twice in the line, the word occurred in the line, and we'll omit the line, that'll be fine.
Yeah, I think that.
I think it's just, yeah, no, I mean, I think we're fine. So this is, that's distributed graph, that's awesome. Let me see if I can, what are some of the other ones? Oh yeah, so like, URL access frequency. And so this is a super common thing at Google, which is like, I want to know, like some of the words in these documents are URLs. When I first started in tech, I worked at this company called Ask.com. It was like in 1999. And a lot of people used to pronounce the word URL Earl. That one didn't have a lot of sticking knowledge, but isn't that weird and gross? Earl. What's the Earl of that? Anyway, I don't know why I just thought of that. Right, so you know, some of those words are URLs, right? And you want to know what the most popular URLs are. Right, so I'm not going to write it out, but that would be actually a mashup of this and this, right? Because you would basically say, you tokenize, but for each word, you'd say, if it matches some regular expression that makes me think it's a URL, right? Emit the URL in the number one, and then sum them up with the same reduce from before. So now I'm not counting words, I'm counting URLs across all the documents, right? So that was too easy. Inverted index. I actually did this one, right, on Wednesday. Maybe what I want is not the word the word lazy occurs 27 times. Maybe what I want is the word lazy occurs in documents 27 and 86 and 42, because later I want to go search the internet based on these term vectors. Right, so I flip this around. It used to be documents containing a whole bunch of words. Now it's an inverted index in the sense that it's words containing a bunch of documents. And as I said, I can go look up lazy and fox, and guess what? Guess what? 27 is the document that I want. Okay? So obviously these are both super common things that Google needed to do. This kind of legitimizes the fact that Google had to invent MapReduce to do the sorts of things that Google needs to do every day, right? What else? Oh yeah, reverse web link graph. again, just a variation on a theme of what we've seen above. Some of the words in documents are URLs. We begin with this thing where you can look up a document, you can see what URLs it has in it. Sometimes you want to go from the URLs to the documents that, you want to go from the URLs to the documents that point to them, right? Google uses this because, a web page that is referenced in a lot of other web pages must be an authority or something like that. And they're going to rank that document higher than others, even though other documents might have a closer match on the actual terms, right? So you would want to say like, nytimes.com happens to point into, UCSC/Palborough or something like that. So that guy must be really important, right? Because, so you want to generate some list like this. How would that work? Let's see. So the map function would output target and source pairs, and the reduce function would concatenate the list of all the source URLs. That's all too easy. All right, let's talk about topology.
Just before you go on, the output of the reduce function is given as a list v2. What does that mean?
Oh, that's what it says.
That's what
I
it
mean, like,
says.
it could be a lot of things, as we saw, right?
So it's just some value that we make up.
Yeah, well, so for each one of the original K2s submitted by map, it can give you in a list context or a scalar context, whatever you want to run in that.
Okay.
So we definitely saw that sometimes, look, it's a scalar context, right? So that is confusing, right?
Okay. Not just me.
Okay.
Give me a name tag.
So a client has written a map function and a reduce function, and they've hopefully tested them locally on their laptop before spinning up 100,000 computers to run them. Not the kind of thing we probably want to debug on a cluster, even if most of the other stuff has been kind of swept under the table. So they want to run this pair of functions, map and reduce. Maybe they're trying to count words, or maybe they're trying to create an inverted index. So the first thing that they're going to do is connect to one of the servers in the map reduce cluster. It doesn't really matter which one. But once they've connected to that one server is different from all the other servers. That server henceforth is going to be called the master. And they're going to be responsible for scheduling this computation on behalf of the client and managing the resources, and dealing with fault tolerance, and all this kind of stuff. It's really funny, you'll see this when you read the Google paper, and I hope you'll have a chuckle, that they begin by saying, Google, we're running all these computers, it's like thousands, millions of computers, and they're not very good computers, they crash, we don't spend a lot of money on them. And so, computers are bound to fail. And so you need to come up with a thing that makes progress despite failures. The jobs are long and computers fail frequently. And then they start describing this architecture and like, well, there's this one distinguished computer called the master. But what are the odds that that one's going to fail? So we have this massively fault-tolerant infrastructure, but we just assume that this guy's not going to fail. Which, okay, fair. If there's a 1 in 1,000 chance of a failure, and there's 1,000 computers, there's a 1 probability that one of them will fail. But there's still only 1 in 1,000 that this particular one will fail, right? So it's not like they're completely crazy to say that. They're just a little bit crazy, because if something can go wrong, it will go wrong. And so since then, and in the Hadoop world, a lot of people have done work on replicated via Paxos fault-tolerant masters. And to the best of my knowledge, the first person to do this was me. So there's a paper in Eurosys 2010 called Boom Analytics, in which we say, wow, Hadoop's really a dog. Wouldn't it be cool if the master was high availability? We did that by doing Paxos, and it was easy for us to do Paxos because we did it in this crazy logic language. Anyway, if you're curious, there is a paper. But since then, there have been, there's a high availability to do this. Anyway, there's this special process, the master, who's supposed to be just sort of in charge of administration. Right? And so the master is going to say, well, okay, this job is supposed to run over some input. So let's just mark down as I did before X. It's obviously not all of the documents are going to be relevant to every single job. But the hope is that a great many documents spread over a great many machines will be. And maybe there's documents on these machines too, but I'm having them playing a different role. So the master is then going to schedule a collection of what are called map tasks. The idea is that they're just independent processes running this function in a completely independent way. Remember, this map function, if I'm running it on one computer, running it on another computer, those computers don't have to talk to each other, because this is an embarrassingly parallel function. And so the mapper is going to schedule map tasks all over the cluster. And as I said before, this master is kind of solving this multi-objective optimization problem, where they're trying to schedule the tasks as close to the input data for that particular task as they can. Okay? But also they're trying to distribute the tasks as close to uniformly around the cluster as they can. In particular, they don't want to put too many tasks on any one machine. Does that make sense? Scheduling all these tasks. Now, remember there was this concern on Wednesday about, well, if you just had the machines start up and just process all their documents, and you had multiple copies of the documents for reliability reasons, then you would do work twice, and you would squander resources that you could have done to do other work. Well, the scheduler is going to take care of that. The scheduler is going to make the best effort to only schedule each individual task on each input data item once. So the fact that this input data item is maybe replicated over here doesn't matter, because nobody's going to process this, because the master's only going to ask one person to do the work. Make sense? So that's how we get around not doing, like, we got 2 to 3 to 5 copies of the data, but we don't do 2 to 3 to 5 copies of the work, because then we would only be able to do 1/3, 1/2 to 1/3, 1/5 of the work, right? Okay. So the mapper schedules those tasks as close to the data as it can, but in some cases, as I said before, it might have to schedule a task, let's say, here, that operates over data here. So we might have to do RPCs to fetch the data. Hopefully we minimize that. Make sense? Good. And what does a map task actually look like? Well, a map task is going to read that input data, apply that function, and it's going to, over time, start producing these outputs, right? In this case, in the case of word count, a list of words on the number 1. And so let's imagine this is a computer with a mapper task, reading some input document, and it's going to, into memory, buffer up its outputs, and periodically flush that buffer to disk. Right? So what does the disk have? It has a representation of this list of words and their counts. And that's it. And the task is then going to inform the master of 2 things: that it has finished, and what the name of the file on its local file system is, so that the master now knows about that file. It's going to turn out that the mappers aren't going to communicate directly with anybody. Reducers are going to come after being instructed by the master and ask mappers for their data. Okay? So when the map phase is done and all the mappers have reported back in, and we'll address the issue of stragglers and fault tolerance a little later, the master then begins scheduling so-called reduce tasks. In general, we schedule many fewer reduce tasks than there are map tasks. In large part because we've done most of the work, right? You use a lot of computers to do the massively parallel chunk of work, and then you do maybe an order of magnitude fewer computers to do the combining, because there just isn't that much work to do. And also because you don't necessarily want the answer spread across the whole system. You want it localized to just a few computers if it can fit, right? So we're going to schedule these